Okay, so over the next 30 to 40 minutes, I will be talking about this project that we have been actually, it is a joint work with Deepankar, who is also present here, and myself. So the topic is on the in federated learning about security of the client models. So I'll start with a very brief introduction on what is federated learning. So federated learning is basically a distributed optimization system where there are multiple agents who each of them are holding their own private dataset, and there is a server in some settings. So the agents are connected to all of the agents are connected to the server. The aim is to jointly train a model based on the aggregated data set of the all the clients combined. But the key thing is the data never leaves the agent, and the training happens in an iterative process. So there are, like, depending on the uh, type of the data set and the model that is being trained, there are basically three categories of the federated learning process. So one is horizontal level federated learning, where the features, the dataset features for the across each of the agents, they are same, but the training samples are different. For example, this can be applied when you are trying to get a model of speech disorder, where the features to identify the disorder could be the same across all the kinds, but you have samples taken from different persons. So that is one example. And the other class is vertical federated learning, which is the opposite of horizontal FL. Basically, you have same samples across all the agents, but the features are different. So one such example could be smart healthcare, where maybe the dataset has come from uh, same organization, but each of the participating agents are focusing on different features of that person involved. And the another class is the transfer learning in federated learning, where it could be different samples as well as different features, which is the most general setting. So in this talk, I'll be particularly focusing on horizontal FL, where the features are same across all the data sample, and but the samples are different. Now, this federated learning came up in 2017. It was proposed by this famous paper by McMahon from Google Research, and it was proposed as a primarily as a data privacy paradigm, because the key thing was that the data never leaves the agent. But as it turns out, after almost like a decade of research, that by default federated learning, this existing architecture is not private. So the key thing is that there are, like, multiple entities participating in the federated learning, right? So we have the server, which is doing the aggregation, and there is several agents. So to make the entire federated learning secure, you need, for example, the server to be trusted, the agents has to be trusted, and there is also a communication link between server and agent. So that communication channel has to be reliable also. So all these things, once all of these are secure, then only you can think of saying that, okay, the federated learning is secure. So in this talk, I'll be focusing on one particular aspect of this, where this communication channel between the server and the agents, that is not secure. Basically, someone else is a third party who is eavesdropping on the channel. So in the landscape of federated learning system research, so in this talk, I'll be focusing only on the, let's say, privacy aspect of the federated learning. So previously, like, people have explored what kind of vulnerabilities are there in terms of data leakage. So they have been categorized as two kind of leakage. One is your shallow leakage. Shallow means the attacker is try to get a sense of membership, inference, or property, which is like not leaking the full all the features of the dataset or all the entire data sample, but some features of it, or whether a particular data sample was actually used in the training for a certain agent or not. That is called a membership inference. But the more uh, deep kind of leakage is where the entire training sample or multiple training samples of the agents are leaked to the attacker. So for example, in image classification problem, that could be pixel wise leakage, and in language model, that could be like a token wise reveal of the training set. But all this literature only focused on data leakage in predictive learning. But remember that there is also a model of the uh, that has been flowing throughout this predictive learning training process, and which has not been discussed so far as much as training leakage of training data has been discussed. Now, just to summarize, what kind of defense strategies are there for the particularly only for the data leakage problem? So there is this classical cryptographic based method like homomorphic encryption or secured aggregation. But the downside is that they incur a large amount of computational and most importantly a large communication overhead, and that is not very good in predicted learning, because predicted learning came up as a low communication cost paradigm. Second kind is your differential privacy, that guarantees that if you incorporate the differential privacy while doing the training, it guarantees that your data will be safe. But the downside is that your model utility goes down. So there is this well-known trade-off between utility and privacy. And there is some other heuristic methods where people have shown that they also helps in maintaining the privacy of the client data based, so that it does not leak from the communicated gradients between the server and the agents. Now, in this talk, I'll focus on, as I mentioned, that the attacker can come from three different locations in the federated learning architecture. So I'll particularly focus on the third party, which is an outsider who is eavesdropping on a particular communication link between a client and the server. And also the attack can happen either in the training phase or in the prediction phase, that is in the inference phase. So my focus is on talking about the security of the or confidentiality of the model. And previously in the not for federated learning but in general machine learning, this model extraction attack has been explored, but that has also only been done in the inference phase. Like you have the API available after your model has been trained, and the attacker has access to that API, so he can send unlimited queries and get the response. And from this query and response, they try to get a estimate of the actual model that is inside that API. But there has not been any research on model extraction attack in training phase in predicted learning, which is going to be the focus of my talk. So this is the problem setting. So we have a horizontal federated learning architecture, and there is an adversary which one of the client is vulnerable. That means the adversary is monitoring the communication channel from that client to the server. And the adversary, we model the adversary's eavesdropping as a uh, binary variable where there is some probability that not at every iteration the adversary may or may not get successfully eavesdrop. If it successfully eavesdrop, then we'll assign that variable to be 1. I'll describe that later. And if it does not, then we'll assign that variable to be a 0 value. So the data privacy, the importance of data privacy, that is obvious, right? We want to protect our own data. But why do we care about model protection? Because the model in this case or in any optimization problem, result represents the solution to some decision making problem, which will be the final outcome when your training is done. And if someone is eavesdropping on the model, on the communication link, and get a good estimate of this model, then without having to do the training, they can just free write in a cheaper way to get this model. And also, if it is an enterprise federated learning architecture, this model represents some IP. So there is a chance that the IP will be exposed to some outsider. So these are the reasons that makes the model confidentiality a considerable a problem of importance. Now, talking particularly about horizontal federated learning. So during the training phase, there are a number of algorithms available, like federated averaging, which is the most basic form of learning technique in federated learning architecture, just a form of gradient descent in this setting. And after that, several other algorithms came up which tried to improve on this basic algorithm. So in this presentation, I'm going to classify these existing horizontal federated learning training algorithm into two classes. One I am going to refer as federated learning with innovation process. Innovation means that instead of sending the entire updated model from the client to the server, only the difference between only the update is sent, not the full model. So, for example, that can be just the accumulated gradient at the current iteration. So those kind of federated learning algorithm I term as flip. And the other one, where each of the clients are sending the full model after they have updated the local model to the server at every iteration, that is classified as flop federated learning without innovation process. So next, over the rest of the presentation, I am going to now try to focus on what kind of vulnerabilities are there in these two classes of algorithms. So just the key point is that we'll see that the flop type of algorithms, they are zero protected. There is no protection in the model of these flop algorithms. And for flip algorithms, we'll see that there is some amount of inherent protection, and we'll try to quantify what is the amount of protection given a number of parameters, like the design of the algorithms, the capability of the adversary who is eavesdropping, and how frequently a client is being selected in the federated learning process, how all of these factors are influencing the protection amount for the flip category. And if there is time, then I will talk about one particular technique that can be utilized to increase the amount of protection for both of these classes of federated learning algorithms. Particularly use a form of dynamic quantization. And the results that I'm going to present next have been published in these two papers, one in last CDC and another one is basically the quantization part that has been accepted for this year AI stats. So since we are interested in protection of the model, so I need a metric to quantify the amount of protection. And I am choosing this as a metric where XCT is basically the client weight, C is for client at time t, and XAT is the estimate of this client model by the adversary. So whenever you see superscript A, that is adversary, and C is for client. And this Euclidean distance between two, that is my chosen metric. So this metric has also been used in existing similar kind of papers in also in general distributed optimization problems also, like you can find it here. And as I mentioned, that I will try to quantify that at asymptotically what is this amount of protection in terms of different parameters, like uh, which are influenced by the adversary side or the federated learning algorithm side, or maybe a combination of both. Now, some technical details. So let us first look at what is the federated learning algorithm that is being implemented in the flip setting. So at iteration k, this is the update rule of the client C, and each client does a number of inner iteration, let's say capital K number of inner iterations, and after the inner iterations are over, so this will be the accumulated gradient, which I am denoting here with this variable psi at time t. And equivalently, you can also represent this model of the client at time t plus 1 after this inner iterations are over in terms of this dynamics on the extreme right hand side. So you can see there are a number of new variables here. So what is delta t? Delta t is the a binary variable. It is either 0 and 1, denoting that whether this particular client C is selected by the server to participate in the training process at time t. And what is psi t? Psi t is just the increment or model innovation. And what is this psi t? Zeta t? Zeta t is the model mismatch between your client and the server. So why this mismatch is important here? Because of this delta t variable, that not all the clients are going to participate at every time. So whenever this client is not participating, he is now don't have the latest update from the server, and that creates this mismatch. Now this is happening at the client side. So what is happening at the adversary side? So the adversary's goal here is to estimate this XCT. And we assume that the adversary has the knowledge of the delta t. That means it knows when the particular client that he is monitoring is being selected by the server. So adversary has knowledge of delta t. And as I mentioned, that adversary's eavesdropping model is probabilistic. So there is a probability gamma based that with probability gamma, it successfully eavesdrop, and with probability 1 minus gamma, it does not get case to eavesdrop at time t. So I am not saying that this is like a only possible or very strong algorithm, but we have seen that this works. So what is the idea beyond this adversaries reconstruction attack algorithm is to mimic this client dynamics of the compromised client. So if you look at the client dynamics, it is XCT plus 1 is XT plus something. So accordingly, we build the adversaries estimate at T plus 1 based on XCT plus delta T into some ZAT. So if I want to mimic the client, my ZAT has to mimic this psi T plus zeta T quantity, which I do in the next two lines, second and the third line. So whenever the client is selected, whenever the eavesdropping is successful, that means mu t equals to 1. So these second components in second and third equation vanishes. And you can see that ZAT is just psi AT, zeta AT plus psi T. So we have this actual thing here that is mimicked here. But the question is what happens, what does the adversary do when it is not eavesdropping the communication between the client and the server? Basically, it does not get what is exact psi t at that particular t. So what it does is we make the adversary look at the past history of zeta t, and based on the past history, that means the most recent time when that particular client was selected, based on that, it does some estimate update of the ZAT variable. Basically, and that update is done in the third line of this adversary dynamics. So there is a intuition that why we came up with this psi-AT dynamics. So I'm not going into the details, but if you look at the actual model increment for the client, what is happening and the federated learning algorithm side, you will see that it depends on this expression approximately. So what is this expression is telling you? It is telling that the psi-t variable, the model increment, is dependent on the model increment the last time it was selected, and also the model mismatch between the server and the client. Additionally, each of them is multiplied with a matrix which depends on a number of quantities. What kind of quantities? It depends on the overall client selection mechanism, the local objective function for each client, and also the dataset at also the other clients. But in our problem, at least here, we are assuming that the adversary is monitoring only one particular client. It does not know what is happening at the other clients. So estimation of this ATT quantity, A and both A and B quantity is very difficult for this particular adversary model. So we don't know how exactly the adversary will be able to do this, but we know that it follows this kind of dynamics. So we just take a simple matrix M, which we keep as constant for now, as a proxy for this A, T, and T hat. And also the for the adversary perspective, it is difficult to estimate psi t also, zeta t also, because as I mentioned, zeta t depends on the information at the server and also at the other clients, which this particular adversary model does not have access to. So in theoretically, we keep zeta t unknown. That means we don't specify what is the adversary dynamics for this estimate of this model mismatch zeta at, but that is included in our analysis. Now, what kind of guarantee do we have for this flip kind of algorithms protection in the model? So let us define an error, which is basically this xct minus xat, and based on this adversary dynamics and the client model dynamics, you can come up with a recursion of the error. And we want this error dynamics to be stable, because if it is unstable, then you have infinite number of protection. So we make sure that the adversary dynamics is stable, for which we need this necessary condition on the eigenvalue of the matrix. And it depends on two quantities basically. One is P. What is P? P is your client selection probability, and gamma. Gamma is basically the success probability of eavesdropping by the adversary. Now, under this condition, we have managed to find a lower bound on the amount of protection at asymptotic in the asymptotic sense. So on the right hand side, you have like a finite non-zero lower bound on the protection. And you can see that there are like multiple terms affecting it. For example, P and gamma is already there. And the influence of P and gamma is almost like intuitive, very, very simple from the expression. But the difficulty is that it does not explicitly tell you how these other variables like model mismatch or increment by the client, how that is exactly affecting this lower bound of the protection. So we try to get a sense of this by making a special case where instead of saying that the adversary is eavesdropping mechanism is probabilistic, we make sure that it eavesdrop with every time with almost in the almost sure sense. So if that is the case, when mu t is equal to 1 for all t, then instead of this inequality, you get an exact expression for this protection amount, and it only depends on your client selection probability p plus this quantity rk, which is I think defined here. It is just the difference between your actual model mismatch and the estimate of the adversary for this model mismatch. So what is the significance of this expression? So you can see that because the adversary is eavesdropping at every time, so whenever the client is sending some information to the server, it eavesdrops that. So that is why this model increment does not influence your protection, because it is monitoring all the CITs, all the zeta t's. And if you look at the expression of the protection, there are two quantities, and you can, because it is the summation of these two quantities, it is not necessary that having this x0 minus x0 to be 0. It is not necessarily the best choice from a defense perspective. And the best thing is that if you have an estimate of this quantity, then the server can compute what is the best p star which will maximize this information, maximize this amount of protection. So in both cases, we can see that there is some inherent amount of protection in the flip kind of algorithms. Now, what happens when the flop type of algorithms, where instead of uploading just this zeta t, now each of the client is uploading the entire xct. So if you recall the previous adversary dynamics, which is exactly these three equations. Now let us look at the adversary's estimate xat plus 1 for this flop kind of algorithms. So I just substitute these other variables into the first equation and get this expression. So we have 4 terms here, right? Basically, various combinations of mu t and delta t. Now, if this p and gamma, basically the client selection probability and the adversary eavesdropping probability, if they are non-zero, then there will be at least some t if you wait for large enough, when both of these variable becomes 1. When both of these mu t and delta t are 1, you can see that the second and the third component vanish. And let's say the adversary is not doing any estimate of the model mismatch. So psi t, the adversary has set that to be 0 for all time. So the last component is also vanished. So all that is left is the first quantity. And because mu and delta are 1, so xat plus 1 becomes exactly xct plus 1. So that means the actual model that the client has sent to the server, the adversary has that exact value. So that means you have 0 protection for this kind of algorithm. So that is why I mentioned that the flop algorithms have no protection under this adversary model. So how much time is left? Or if anyone has any question at this point, I'll be
So first, on the time issue, so we still have half an hour to go. So you're pretty safe. All right.
Oh.
You can even go a little bit slower. I think you're only like 5 slides away. So, all right. Yeah, of course, depends on your pace. Yeah.
Okay, great. So that brings me to the end of the first part, where so far I have tried to uncover the existing vulnerability in federated learning when there is an eavesdropping attacker in the communication channels, and try to get what kind of protections are offered by these flip and flop type of algorithms. Now, so far there has not been any defense mechanism from the client side to improve this amount of protection. So I have only just give the expression for the existing protection without any defense mechanism. Now, the question is that, particularly because flops have been shown to be totally unprotected, so can we increase this protection for flop and possibly also for flip? So to answer that question, that brings me to the second part of the talk, where we'll utilize quantization to improve this protection. So quantization, as we all know, is primarily a mechanism for saving the amount of communication that is being sent in this federated learning scenario from the client to the server, and also back from server to client. And so in case of quantization, the client don't send the actual model or the actual increment psi for flip, and for flop not the actual xct, but some quantized version of it. So quantization is, if you look at the quantization mapping, so it is a mapping from the real numbers to some set of integers. How many integers, that depends on how many bit you are allowing to transmit. if you have b bits, there will be like 2 to the power b total levels of 2 to the power b number of beans, which splits your interval starting from q min to q max into a certain levels, and depending on where your actual value is, you send the, in this case, the floor of that particular interval. And so this, instead of sending the actual x, the clients will send the quantized qx. The server will receive this qx, and from this qx it will recover the decoded version of this x, which was the original x that was computed by the client. Now in this case, this decoding will not be exact, so there will be some difference between your xq and actual x, which introduces you to the quantization error. Now in this scenario, we will utilize this quantization error to actually increase the amount of protection. So that is the idea. But so this is the setting for uniform quantization. But the downside is that whenever you do quantization, your protection might be increased, but at the same time, your accuracy of the model, that will go down. So to preserve this accuracy or utility of the model as much as possible, we implemented dynamic quantization. So where does this dynamic nature is coming from? So it is coming from the interval that you are selecting inside which you are doing the quantization. So basically this q min and q max. So let's say this, I said I am, the midpoint is at 0, and I set the q min to be some minus beta and q max to be some plus beta. So that is my interval inside which I am doing quantization. Now, in case of dynamic quantization, I am allowing this minus beta and plus beta to be dynamically updated at every global round. So how do I do this update? So one very simple way to do that is, let's say at time t, you have some beta t. So this update of the beta t is done at the server end based on two conditions. One is, if any of the client at the current time t, if there is some saturation. So what is saturation? Saturation happens when your actual model value is outside this interval. So it can be either less than minus beta t or greater than plus beta t. So whenever one of the client runs into saturation at current time, they indicate that saturation by a binary variable, which I denote with theta it. I is the client index, t is the time, current time. So the client knows that when it's doing the quantization, whether saturation happens or not. So it communicates whether the saturation has happened or not to the server by this scalar variable. The server receives all the scalar variable from all the participating client at the current time. And if there is no saturation, the client reduces the range of this quantization. So alpha 2 is less than 1. That means whatever interval was there from minus beta to plus beta, now at the next time there is going to be a shorter interval. And if saturation has happened, that means whatever existing quantization range is there, that is not enough. So I need to increase the range more. So it increases the current beta t with some positive factor alpha 1. So that is the idea of dynamic quantization. And if you look at the communication overhead, that is coming only from the quantization side. So if you look at the client side, to implement this quantization, the client complexity is order of d. Just the client need to do only this qx, and this qx will be sent to the server. Server will have to decode, and the server will have to decode this qx for all the participating clients. So if there is modulus of st number of clients participating at round t, then the server complexity is d times that number of clients. So here d is the number of dimension in x. So x is basically lying in the real space of dimension d. So that is the communication complexity due to quantization. And if you look at the communication complexity, so in the uplink, each client is sending b bits for each scalar quantity, and because x is a vector, this quantization is implemented component wise. So for one scalar component b bits, so for d vector it is b into d plus this binary variable, so total is b into d plus 1, so which is still order of d. And if you look at the downlink, so we are assuming that the quantization is being done only on the uplink, so the server is not doing any quantization when it is sending back the updated models. So if the full precision is 32, it is going to be 32 into d plus 1. D is for the full model, and plus 1, it also needs to give the updated beta t back to the clients, which will be used in the next step when the client again performs a quantization. So this is again order of d. So all the overhead coming from the quantization are order of d. So that means it does not increase your federated learning algorithm complexities, because to send the gradients you need always at least order of d number of information. So that is why it is very lightweight. Now next question is, what happens if you implement this dynamic quantization for flip and for flop? So first let us look at the flip dynamics. So before quantization, we have this adversary dynamics on the left hand side. Now I am doing some simplification. Like I mentioned before, that estimating this model mismatch psi t is very difficult. So for now, let's set psi t to be 0. The estimate of psi t by the adversary to be 0, which is this red colored part is 0. This matrix which was used in updating the estimate of this zeta t when the client is not able to eavesdrop at the current time t, this matrix m, we also said that very simple to be just some diagonal matrix with positive value m. And we assume that the adversary is strong in the sense that it knows what is the communicated beta t variable also, because that is also being shared in the channel. And based on this information, the adversary dynamics can now be written like this. So I have just removed the zeta t part, and I have set m to be small m into a identity matrix, which gives us this adversary dynamics. So one important thing here to note is that because the adversary knows what is beta t, so only regarding quantization, the adversary has the same amount of information as the client has for decoding. So based on whatever QX the client is sending, the XQ at this adversary's end and XQ at the server end are going to be the same. Under this adversary dynamics, I define the reconstruction error similarly as before. XCT is the actual client model before quantization, and XAT is the estimate of the adversary. Error is the difference between these two. Now we also have this quantization error coming from this step, which I define to be psi t, because in this flip case, you are sending the psi t's, not the full model. And the psi t's are which are quantized. So the quantization error at time t is going to be the difference between your quantized value and the actual value of the model innovation, psi t. Yeah. And to if you look at the perfect eavesdropping scenario where the client adversary is able to eavesdrop with probability 1 at every time, then we have obtained this lower bound on the amount of protection. So the first expression is for any time t. So if you look at the component, so there is a decreasing quantity a. A is lying between 0 and 1. So at t goes to infinity, this component will vanish. And it is coming only from the initial mismatch of the reconstruction error. So also if both the adversary and client somehow start from the same point, this component is going to be always 0. Otherwise, there will be some component for finite times. And the second component is like a convolution between your A and B. So what is B? If you look at B, there are two important quantities here. One is the expected value of the model mismatch, which happens because the clients are not being selected at every time due to that probability P. And the other component is purely coming from the quantization error. So when this quantization error is not there, you can see that this component, the second component will be 0, and BT will be just this due to the model mismatch. But when we introduce any quantization, you have a positive influence on the amount of BT, and that means you have a positive influence on this lower bound of the T square. So that is why when you do quantization, your protection of flip always improves for all finite time. Now, what happens if T goes to infinity? So this, because A is between 0 and 1, this component will vanish, and you will have something like B divided by 1 minus A. So if you assume that the model mismatch is persistent, and the quantization is also persistent, in the sense that even if you go to asymptotic sense, you never let the quantization to be off, and the server always chooses not all the clients but only a subset of clients. So under these two conditions, which is quite uh, practical, you can show that the asymptotically the amount of protection will be lower bounded by this quantity. So it will have at least this amount of protection. So you can see that the lower bound has a negative sign. That means it is possible that when your this delta zeta and delta psi are nearly equal, so they might cancel. And actually, this is a valid lower bound because we have used Cauchy-Schwarz inequality. That is why when they are in the opposite direction, they might cancel. But in practice, it is very less likely that they will be exactly in the opposite direction. So that is for the flip. Now, what is the effect of this dynamic quantization on flop? So if you look at the adversary dynamics, so previously, without any quantization, we had that xat plus 1 is actually xct plus 1 for at least some t. If you wait long enough, that means you had zero protection. But now we don't have xat. We have this quantized version of qt, and that's why if you look at the final expression of the protection at any t, we get to recover the protection exactly in terms of this equality. So there are two components. One component is coming from the initial mismatch between the adversary's estimate and the actual client model, which is E0. And P is the probability that the client is being selected at round T. And again, the second component is coming from a convolution between your this A and B. So in this case, there is no model mismatch here. Only the quantization is responsible for this convolution term. So you can see that when T goes to infinity, only the effect of the quantization will be present. So there will be no delta psi component here. So that is why quantization helps flop to have a non-zero protection amount, which was not possible without quantization under this adversary dynamics. So these are the theoretical results. So I have just two more slides to show that how it works, how this dynamic quantization works in simulation. So we did a number of experiments, but here I am just showing the one particular of them, which is the C400 dataset, and each client have a resonant 18 model. Because it is federated learning, so the dataset is supposed to be non-IID. So we split the dataset, the entire C400 training dataset, with a Dirichlet distribution with some coefficient. So we are mimicking a non-IID scenario, and we said a large number of clients, like 1,000. And regarding the quantization parameters, so we have alpha 1, alpha 2, which is the increment or decrement of this range of the quantization. We set that to be 1.1 and 0.9. we are using 8-bit quantization from client to server, and from server to client, it is full precision. Gamma equal to 1 means that the adversary is eavesdropping at all time. That means mu is 1 almost surely. And the federated averaging algorithm is being implemented, which is just simple SGD. And every global round, the client selects the server selects only 10% of the clients, which is 100, and mute equal to 1, like I said. Now, if you look at we compare the accuracy on the test dataset from the client model and from the adversary model with and without quantization. So if you look at without quantization, uh, this is the cyan colored line for the adversary's estimate. So we let them start from the same point, but you can see that after uh, like 50, 55, 50 or 60 iterations around, the test accuracy drops significantly to settle at 1%. 1% because it is a super 100 data set, so there are like 100 classes. And if you have a random model, the prediction accuracy for each classes is going to be like 1% only. So adversary is brought down to that level after some point. And if you do quantization, which is this purple color line, you can see that the drop happens even before that, like at the very beginning, almost like after 10 iterations. And what happens on the client side? So there is some model utility loss, but it is not too significant. I will present the number in the next slide. So this is for the flip. And what about the flop? So if you look at the flop adversary dynamics, which is this without quantization, which is this cyan colored line, and the adversary's actual test accuracy without quantization, which is the dotted orange colored line. So they indeed overlap here. And that is what we predicted from the theory also, that flop is zero protected without any quantization, which we can see here actually. And if you implement dynamic quantization in this setting, so the adversary's estimate drops again significantly from like a perfect estimate to nearly 1% accuracy. And there is also a drop in the model utility between this dotted green curve and dotted orange curve. So how much utility loss is there? So all these are uh, tabulated here. So we did also some experiments on a simpler data set to basically get a feeling whether how the theoretical results that we have, whether they match to the simulation or not. Because with a larger data set, it is uh, difficult to do like a ablation studies to verify the theoretical results. So we also used a smaller data set and a smaller model and looked into different scenario, like what if you reduce the number of, what if you increase the client selection frequency from 50 clients to, let's say, 8 clients, or what if you change this beta update factor of alpha 1 alpha 2 to, previously it was 1.1.9, what if you increase it by 20%, like 1.2 and 0.8, what if you increase the number of bits and so on. So in each cases, you can see that for flip algorithm, the adversary's accuracy is quite low. But if you look at flop algorithm, the adversary's accuracy, so this is the final accuracy. And we ran this simulation 5 times because there are some stochastic variables there, and took the mean. So these values are the mean over 5 runs. So if we look at the flops, the adversary's test accuracy without quantization is like 60, and the client also is like 60.9. So very almost zero protection. But that is not the case for the flip algorithms in all different scenarios. On the other hand, if you do quantization, the adversary's flop accuracy drops from 60 to 10%. 10% because it is cipher 10. So a random model's test accuracy will also be 10%. and similarly for C400. And regarding quantization, what is the amount of utility loss? So if you look at C400 for flip, the global model's loss is not too much. So it is just 39.53 to 39.21. But it is more in case of flop, because in case of flop, you are quantizing the full model. But in case of flip, you are quantizing only the increment. The increment is smaller in magnitude. And the effect of quantization, that in case of a smaller variable, that also is not too much. So for flop, you can see that there is like almost 4% drop in utility, but you get very good amount of protection, like which previously was 35, now it is just 1% test accuracy by the adversary. So that brings me towards the end. So to summarize, we looked into the under researched area of the model confidentiality in federated learning. And this is a part of our broader research plan where we are looking into securing distributed optimization without compromising the model utility, or that means preserving the utility as much as possible, but in with that constant how much protection or security you can get in the models. So in addition to federated learning, we have also looked into recently in general distributed optimization setup with a peer-to-peer communication graph. And we have some result published accepted recently in this International Journal of Robust and Nonlinear Control for the distributed optimization protection. And we are also looking at what happens if there is in practical under practical scenarios, like what happens if there is packet drop between the clients. And in the federated learning side, there are still a lot of work to do. For example, in this talk, I have only talked about the adversaries monitoring only one particular client. What happens if it is monitoring multiple clients at the same time, or there are multiple adversaries, each of them monitoring one client, and they are colluding between themselves? So certainly that is going to make the model protection problem challenging. So can we come up with some protection to how can we ensure protection in those scenarios? Also, this entire discussion I have focused only on passive adversaries, means that the adversary is honest but curious. So it is trying to estimate the model but not going to affect your actual FL algorithm. So on the other hand, there are active adversaries who not only estimates your model but also try to affect this federated learning algorithm during the training phase by injecting, let's say, uh, backdoor attacks or poisonous data set. So how can you guarantee that your data set or model will be secure in such active adversaries? So there have been some number of research going on in this scenario. So we'll look into that also. And I will also look into the at the very beginning of the talk, I talked about data privacy of the model, which was basically this is a inversion problem from gradient to recovering the data by the adversaries. So if, when I presented the existing well-known defense mechanism, so we talked about these 4 or 5 things, and we want the defense mechanism to be not computationally or communication heavy. We want a simple thing. So, and differential privacy also reduces your utility of the model. And on the this heuristic kind of method, there is no guarantee that your data is going to be secure from the gradients. So can we still preserve data privacy from gradient leakage without compromising your utility of the model? So I am looking into those kind of questions as well. So that's all I have for today. And